All right, hi everyone. Welcome back to our material and energy balance lecture here. Today we are going to be switching gears a little. So far we have been doing a lot of our material balance questions. Now we're going to take a step back and do some more fundamentals first before going back into that. Today we're going to be in section 5.1 and 5.2. There's pages 218 to 228 from the textbook. So go ahead and read that up first before starting this video. Before that, I talked about using the degree of freedom analysis, source of independent equations as sort of my outline for this entire course. So let's go back and revisit that. The sources of independent equations in our degree of freedom analysis, the first thing we have was counting the material balances, so number of species equals the number of balances. We did that. So that was in chapter 4. For energy balances, we know that we're going to get to that towards the end of this class, so we're not going to do that yet. We have looked at a lot of process specifications, so we have that. We have briefly mentioned physical properties and laws, but that's actually where we're going to go for the next two chapters. We have looked at physical constraints. Some of mole fractions, some of mass fractions have to be equals to 1. And just most recently, in the past few lectures, we have been doing chemical reactions, so we have used stoichiometric relations. So where we are going with this in this class in chapters 5 and 6 is to look at physical properties and laws. In chapters 5, which is what we're covering today, is going to be a single-phase system, and in chapter 6, we'll look at multi-phase systems. So why do we want to look at physical properties and laws? Why is that important? Practically, in a lot of our flow meters, what we are actually measuring is volume or volumetric flow rates. Practically, that's the easiest measure that we can have. But when we do our material balance problems, we cannot do a volume balance. We have to either do a mass balance or a mole balance. So we need a way to convert from our measured value of volume into mass or moles. And so we came across this triangle in our earlier lecture back in chapter 2, the way to convert between volume to mass and then mass to moles. Between volume and mass, we know we can look up the specific gravity in table B1 and use that to convert to a density. Between mass and moles, we can simply use our molecular weights. We briefly mentioned we can go from V to N directly, and this is known as a specific molar volume. This idea of a V hat, specific molar volume, by definition, is the volume occupied by 1 mole of a substance. So volume divided by moles. If you think about going through this triangle, going through mass and then getting to moles, you can also rewrite V hat as a function of molecular weight and density. So V hat, by definition, is V over N. It is also equal to your molecular weight over your density. Molecular weight is simply, you can look that up using a periodic table or look that up by some source. It is not a function of your temperature and pressure, but what we want to focus on in this lecture is that this idea of density may be a strong function of temperature. So going back here, I'm just repeating the equation for a specific molar volume. We're going to look at first solids and liquids and then start to look at gases. In solids and liquids in general, density is a weak function of temperature and pressure. By way of illustration, for example, we have the density of water at 1 degree C and density of water at 99 degrees C. So we're spanning almost the entire range of temperatures where water is liquid, right above freezing and right below boiling. And you can see by the density values down there, going from this entire temperature range, you are only looking at a difference about 4% in your density values. So in general, for solids and liquids, we are going to assume a constant density. We just look up the specific gravity and assume that that value is going to apply for any of the temperature and pressure that we are using. For gases, on the other hand, density is generally a strong function of temperature and pressure. Again, as an example, I'm losing the density of air at 0 degrees C and 100 degrees C. So about the same temperature range there. And what you see here is more than a 25% difference in your densities as you increase the temperature from 0 to 100 degrees C. As such, you cannot just look up a density value from some book and use it for any temperature. You actually have to use what we call an equation of state to estimate our specific molar volume. And we'll get to this idea of equations of state at the later part of this lecture. So now let's go back to solids and liquids, make a few more notes about that before we move on to gases and talk about equations of state. In our solids and liquids, like I mentioned earlier, we're going to assume constant density of the individual components, look up the specific gravities in table B1, convert it to your actual densities, and we can use that value. What happens if we have a liquid mixture? So for example, let's say I'm mixing 50 mils of ethanol with 50 mils of water. What is the density of that mixture? There's two ways you can calculate the density of a liquid mixture. The first way is using the mass average of the individual component densities. So all we are doing is weighing the individual densities with the mass fractions. In equation form, this is what it is. You have the mass fraction of your species 1 multiplied by the density of species 1. You sum them up for the different species, and you have your average density of that mixture. So that's the first method you could calculate the density of a mixture, liquid mixture. The second method is assuming volume additivity. So what this means is if I have 50 mils of ethanol and I add 50 mils of water and I pour them together, I'll get 100 mils of that solution. You might remember from your general chemistry that volume additivity does not always apply. This is related to the fact that your different components might have intermolecular forces that will change the volume. So 50 mils of something plus 50 mils of another thing might not give you 100 mils. If we assume volume additivity applies, you could make some convergence, do the math, and actually show this is how you can actually come up with the average density of your mixture. So the reciprocal of your average density is the sum of your mass fraction of that component divided by the density of that component. Sum them all up, that will give you the reciprocal of your average density. So the question is, when do you use which method? There is no hard and fast rule, but in general, we would use the second method if we know all the components in our mixture have similar molecular structures, which means the intermolecular forces are about the same. And because of that, the volume additivity assumption is going to be valid. The method B is going to be more accurate. All right, so now we have looked at the solids and liquids. All we need to do is assume a constant density, look up a table, look up the value in a table, and presented two ways of looking at the average density. So let's go to gases. We say that gases, the density is a strong function of temperature and pressure. What we need to do now is to use an equation of state. What's an equation of state? It is an equation that relates the number of moles, N, and the volume it occupies, V, to the operating conditions, temperature and pressure. The most common equation of state that most of you are probably familiar with is the ideal gas law. PV equals to nRT. If we look at volumetric flow rates, it's PV dot equals to N dot RT. I can manipulate this equation by dividing by either N or N dot, and we end up with this specific molar volume that drops out. So PV hat equals to RT. Again, we want to know what this V hat is, so simply we can just rearrange this equation. V hat, for an ideal gas, V hat is just RT over P. Here you can see how the specific molar volume becomes a function of temperature and pressure for a gas. This idea of a V hat allows us to convert from our volume to number of moles. What happens if we just want to convert from volume to mass? We don't want to go to moles. We need our density. Recall that V hat is also molecular weight over density, so we can make that substitution, rearrange it for density, and we can come up with this equation. Again, here you can see how density is now a function of pressure and temperature of the operating conditions of that gas. So this will allow us to convert between volume to our mass. Note that in all these ideal gas equations, the pressure is absolute pressure. So if your measurement is in a gauge pressure, make sure to add your atmospheric pressure to it to get your absolute pressure before putting it into these equations. All right, so moving on to the next concept here, we can think about our specific molar volume at standard conditions. So standard conditions typically is defined as 0 degrees Celsius and 1 atmosphere. We can use our V hat equals to RT over P, but in this case, our T is just the standard temperature, P is just the standard pressure. I'm going to do everything in SI units, so I'm using Kelvin and Pascals. You'll end up with this standard V hat value. Some of you might have seen this before in your general chemistry, this idea of a 22.4 liters per mole. So this is the standard specific molar volume under the conditions of 0 degrees C and 1 atmosphere. One more concept here. This is a new concept of a definition of volumetric flow rate. You might see this in some of the problems. SCMH, SCFH, one is just in SI units, one is in English units. SCMH is standard cubic meters per hour, and SCFH is standard cubic feet per hour. What this is the volume or the volumetric flow rate at standard conditions, not at the operating conditions. Whatever operating conditions you have, this is the flow rate if you took that flow rate and converted it into the standard temperature and pressure of 0 degrees C and 1 atmosphere. Sounds confusing? So let's use an example. Hopefully this will clarify everything. So in this example, we have a stream of butane gas. We have a flow rate of 3.95 times 10 to the power 5 standard cubic feet per hour at 285 degrees Fahrenheit, 1.3 atmospheres. So it seems like there's two sets of conditions given here. There's the actual operating conditions, which is 285 Fahrenheit, 1.3 atmospheres. The flow rate that's given to you right there, 3.5 times 10 to the power 5 cubic feet per hour, that is if it was translated into 0 degrees C and 1 atmosphere. So we want to know what is the molar flow rate, mass flow rate, and the actual true volumetric flow rate. Note that this volumetric flow rate given is not at 285 degrees C Fahrenheit, 1.3 atmospheres. So in terms of the molar flow rate, we know that the volumetric flow rate at standard conditions, that's the definition of your SCFH, is 3.95 times 10 to the power 5 feet cube per hour. So to convert from volumetric flow rate to molar flow rate, we can use our ideal gas law. In this case, the temperatures and the pressures are just the standard temperature and standard pressure. We could put in 1 atmosphere and 0 degrees C and put in the numbers, plug and chug and get the value. Or you can do a shortcut and recognize that this quantity right here is essentially your 1 over your V hat S. The specific molar volume at standard conditions, the 22.4 liters per mole, or you have those different values in different units. If we do that, then you recognize that we can just use a single value instead. So you just take the V dot S divided by this specific molar volume at standard conditions. We are doing everything in English units, so we're going to use 359 feet cube per pound mole. Put that all into here, put it into your calculator, and you get the molar flow rate of this gas. So the second part, we're looking at the mass flow rate, converting from moles to mass. All you need to do is you have your molecular weight. Molecular weight of butane is 58 pound mass per pound mole. Multiply that by our molar flow rate, and we end up with a mass flow rate of 6.38 times 10 to the power 4 pound mass per hour. So note that the molar flow rate and the mass flow rate is not dependent on operating conditions. Whether it is at 0 degrees C, 1 atmosphere, 285 degrees Fahrenheit, 1.3 atmospheres, the molar flow rate and the mass flow rate will not change with operating conditions. What will change is the volumetric flow rate, and now we want to know what the true volumetric flow rate is. I'm going to present two different methods of doing this. The first method is rather intuitive. We are just using the ideal gas law. We know our molar flow rate. We know the actual operating conditions, temperature and pressure. So we can just put it into our ideal gas law. V is equal to nRT over P. We know the n dot from our part 1. We found the molar flow rate. In this case, I picked a gas constant that has rather odd units, mostly English units. So I just want to make sure that everything units-wise is consistent. Once I put this into my calculator, I can get the volumetric flow rate, actual volumetric flow rate, 4.60 times 10 to the power 5. Again, let me emphasize, this volumetric flow rate, 4.0 times 10 to the power 5 feet cube per hour, is the volumetric flow rate at 285 degrees Fahrenheit and 1.3 atmosphere. If I change the operating conditions to 0 degrees C and 1 atmosphere, I will end up with 3.95 times 10 to the power 5 cubic feet per hour. So that's the first way of doing things. I would say that this is more intuitive, but you can see that you have to be careful to keep track of the units and make sure that you have all the units consistent, because R typically has the most complicated units in that, your gas constant. In the second method, what you're going to do is using what I call the ratio method. So in equation 1 is simply our ideal gas equation. Equation 2 is also our ideal gas equation, but at standard conditions, and now using the V hat S, which we know the value of. And I'm going to divide 1 by 2. So now what I get is a ratio of pressures and a ratio of temperatures. And my R disappears. Why is this method easier in a way for calculation? Because number one, we just have to make sure our pressures and temperatures are of the same units, and the units will cancel away. And number two, like I mentioned earlier, in a lot of these ideal gas calculations, where the complication with units come in is through the gas constant. And now we have removed the gas constant, we don't have to worry about that. So now I'm going to rearrange this in terms of V dot, because that's what we're trying to find. And now we have V dot equals to N dot, which we know from part 1. Ratios of temperatures, ratios of pressures, and our V hat sub S, which we know is 359. Now we can put in the values. I'm doing my temperatures in Rankins. I'm keeping my pressures in atmospheres. That's going to cancel away. And once I put in these numbers, I'll end up with the same value. So note, one quick note about this is your temperature ratios. You have to be careful about this. For temperature ratios, you can do it in Kelvin, you can do it in Rankine, but you cannot do it in Celsius and you cannot do it in Fahrenheit. Go back to chapter 2 where we talked about unit conversions of temperatures. Unlike most other quantities where we convert between one unit to the other, we just multiply by some factor. When we talk about temperature conversions, you have to add some constants in some cases. Just for example, up here, converting from Fahrenheit to Rankine, you actually add 460 degrees C. And because of that, the ratios are not going to be the same. So you can take the ratio of Kelvin, ratio in Rankine, but not in Celsius or Fahrenheit. So as you're doing this ratio method, be sure to keep in mind that you cannot do the ratios in Celsius or Fahrenheit. All right, so we have finished our solids and liquids. We have talked about ideal gas, a single component. So we're going to use the ideal gas law to figure out a specific molar volume or density, and how is that a function of our temperature and pressure. Last thing we want to cover is what happens if we have an ideal gas mixture. So to cover this concept, let's do a thought experiment. Let's assume we have a container of volume V. The operating conditions is at some temperature T and P. And in this container, we have three different species, A, B, and C. We have NA number of moles of A, NB moles of B, and C moles of C. If we want to apply the ideal gas law to this system, we just need the total number of moles, which is the sum of all the moles of each component. And we can apply our ideal gas equation. So PV equals to nRT. I'm going to call this equation 3. Now I'm going to introduce a new concept. So this is the idea of a partial pressure. The notation or the nomenclature for partial pressure is small p. Remember, overall pressure of the system is big P, partial pressure is small p, and then the subscript, as always, we're going to use it as the species we're talking about. So small p sub A would be the partial pressure of A. So the partial pressure of A is defined as the pressure exerted by the moles of A only in this very same container of volume V at the same temperature. So do a thought experiment, pretend you can open up this volume, take out every single molecule of B, take out every single molecule of C, close it back up. What is the pressure exerted by A only? That is this idea of a partial pressure. So if we take out the molecules of B, molecules of C, and we just apply the ideal gas equation again to just A, we have now PA, which is our partial pressure of A times V, is just number of moles of A times RT. Using the ideal gas equation, I'm going to take 4 divided by 3 now, and we end up with this equation. The partial pressure divided by the overall pressure is equals to the moles of A divided by the total number of moles of A. But we know what that ratio, moles of A over total number of moles of A is. That is simply our mole fraction, the mole fraction of A. Rearranging this equation, you have what we call Dalton's law, which is something that's really important for you to remember. The partial pressure of any species is just the mole fraction of that species multiplied by the overall pressure. So what happens if we now sum up all the individual partial pressures, PA plus PV plus PC? So let's do that. Here what I'm doing is I made a substitution with Dalton's law for each individual partial pressure. And now you can see I can factor out the overall pressure. YA plus YB plus YC, this is just the sum of mole fractions of every component, so this is just equal to 1, and it will give us our overall pressure. So some of you might find this intuitive. If we sum up the individual partial pressures, we will end up with the overall pressure of the system. All right, we can do the same thing with volume. And we can show what we call Amagat's law. In this case, VA is the pure component volume of A. It looks really similar to Dalton's law, except now we're replacing pressures with volumes. Amagat's law is not as important, and you're not going to see it very often, but you should always remember Dalton's law. That is a law that you're going to see quite a lot in a lot of our separations process down the road in your chemical engineering curriculum. So this is the end of this lecture. We will have one very quick example, just looking at Dalton's law and Amagat's law to give yourself some practice with these new laws. There will also be some review on converting between mass and mole fractions. So go over that example to make sure that you understand these laws. Work hard, be smart. I will see you in the next lecture.